We continue from where we left off yesterday. We continue with our discussion on the ODEs, ordinary differential equations, matrix equations, degenerate systems. We are looking at the kinds of questions we looked at yesterday. This we solved. This one we solved. Okay, there are questions we did not solve yesterday. There's so many, and obviously our attempt is to finish the whole exam paper. Right, so yeah, we had this question yesterday. Right, having had this question yesterday, we need to ensure that we are able to solve this. Right, and to solve this, we continue as follows. So let k be an integer, a positive integer. Use the principle of mathematical induction to prove that if a minus lambda I all to the power k times vector u is 0, then u is an integer which corresponds to the non-repeated eigenvalue lambda of a. Right, so we proceed as follows by mathematical induction. Let k be 1. Right, let k be equal to 1. Then we have that because 1 is a positive integer, so we shall have therefore that minus lambda I, we raise it to the power 1 times vector u is equal to 0. And this actually means what? Yes, please. Okay. Right, so we continue with this, just 1 minute. Okay, we here. And what does this mean? So we distribute, we open up the parentheses and right, this means a minus lambda I times the vector u equals 0. Okay, this is also the 0 vector. Hence lambda, or hence u is an eigenvector, is an eigenvector which corresponds to the non-repeated eigenvalue lambda of a. Okay, we know that that's the statement the statement is true, right? For n equals, for k equals 1. Assume that the statement is true for k equals n. Right, assume that the statement right is true for k equals n. That is a minus lambda I to the power n times vector u equals the zero vector. Oh, that is if this is the case, then if this is the case, so then u is an eigenvector which corresponds which corresponds um right, which corresponds to the yes, Mganami, I'm in class. Is it possible that I give you a call when I'm done? Oh, all right. Okay, thanks then. Okay, thanks, Mgana. All right, which corresponds to the which corresponds to it's exactly this corresponds to the non-repeated eigenvalue. Right, non-repeated eigenvalue lambda. Right, eigenvalue lambda of a. Okay, continue. Next, we just have to prove the last part. So the last part, in the last part, we actually suppose that, or we let, in fact, let k be n plus 1. Then we can write the following expression that we have what is there. So what is there? So it is a minus lambda I a minus lambda I plus 1 vector u. Right, so what is the meaning of this here? What is the meaning of this here? Well, the meaning of this would be it is a minus lambda I lambda a minus lambda I and say 1 times vector u, and this result is 0. So before we said that it is 0, we can just present a small argument. Ah, okay. I've put a lambda on top here. It should be an n. It will be an n. So here we have an n, so that n plus 1 is this. Okay. But what is this one? A minus lambda I to the nth power. A minus lambda I to the nth power with vector u is 0. So now we can manipulate this accordingly and see how best we can actually analyze this. But what is this exactly? Right, there are a couple of schools of thought, obviously, on this. Simultaneously, we have already proven that a minus lambda I u is 0. So it is featuring a minus lambda I u. So effectively, this guy, we already know that this is lambda I n, and we already know that this guy is the 0 vector. With that said, then these cannot survive. The 0 vector times this doesn't matter what it is a 0 vector. The conclusion, therefore, is that the lambda I to the n plus 1 times vector u is 0. Okay. So we have that this is 0. Right. And by the induction hypothesis, we actually obviously used the induction hypothesis together with the initial statement. So that using the principle of mathematical induction, we're able to prove that if, and we're yet to conclude, that if this is 0, then u is an eigenvector which corresponds to the non-repeated eigenvalue lambda of A. Okay. So what next do we say? What we say next is the following. Right. If this is 0, then u is an eigenvector which corresponds to the eigenvalue. We have already seen that it is the case here. And it is as well assumed to be true here. So there are a couple of ways to even justify, because we have that this is 0. Right, and if we have that this is 0, but from here, obviously, this is a minus lambda I. A minus lambda I, okay, u. Right, so this is just a use of exponential laws, that this equals that. Um, and there's more, obviously, we need to say, and there's more we can most certainly say at this point. Hence, from this assertion, we can present our argument as follows. Hence, if K is n plus 1, then we have that the a minus lambda I to the power n plus 1 times vector u is 0 vector, so that okay, hence if this is the case, then this is 0, so that lambda itself, so that according to this statement, so that u is an eigenvector which corresponds to the non-repeated eigenvalue lambda, so that u is an eigenvector, okay, is an eigenvector right, is an eigenvector which corresponds to the non-repeated eigenvalue lambda of A. Non-repeated eigenvalue right, eigenvalue lambda of A. Okay, so the understanding is that the eigenvalue lambda itself is non-repeated. Okay, because if it is non-repeated, it means we have only one eigenvector. Because if ever lambda is repeated, then you can have two eigenvectors. In which case, then the proof is going to take a different turn because you won't be dealing with one eigenvector. They can always be two if it's repeated. So you have the geometric multiplicity. If it's repeated, maybe it's of multiplicity 2. Algebraic multiplicity, it's how many times the eigenvalue is repeated. So under normal conditions for a non-defective matrix, um, if lambda is of the algebraic multiplicity 2, it will follow that we expect the geometric multiplicity to be 2 as well. Okay, so yeah, we continue. We continue. All right. So this is the proof. This is the proof. So this becomes the proof. Okay. This becomes the proof. So we continue. We continue. All right. Okay, I wanted to comment on the I wanted to comment on the what you call the algebraic multiplicity. Right, something called the algebraic multiplicity. The algebraic multiplicity would be Um, okay. Right. So algebraic multiplicity, it's the order, e.g., I'll give an example. Let's find this one. C lambda is the characteristic equation, and it is lambda minus 1 all squared. And this is the eigenvalue. So we shall have that lambda is 1. And this one is the what? Is 2 is the algebraic multiplicity. 2 is going to be what you call the algebraic multiplicity there. Okay, and then now if the lambda is 2, for a non-defective matrix, we expect these to would expect under normal conditions to have a geometric multiplicity of 2. What would a geometric multiplicity of 2 mean? Right, and that would mean that we have 2 eigenvectors. So yeah, so this proof, it's a proof for an unrepeated eigenvalue, so that we have surely 1 eigenvector that is corresponding. And the proof, therefore, it's done with ease. All right, multiplicity. Now, next. Okay, next question. So we have this. Okay, this one we did yesterday, the eigenvector eigenvalue method. It came from the exam paper. We actually solved it. So no worries there. Moving on to the next unsolved questions that came from the paper. Let's see. Okay, we also have this one. This one is also book work, so we can just have a brief discussion on it because it normally comes in the exam. So right, we're looking at this proof, please. So just in a second. Okay, if f is continuous and now phi itself is a fundamental matrix of the matrix of the differential equation, then show that a particular solution of the non-homogeneous system is given by this. Let's look at the, and this one is called, yeah, the particular solution there. Let's look at the proof of this. What is the proof? We have to show that xp dot, we have to show that xp dot of t so we have a of t plus f of t. Since phi itself, so we have to show that x dot is this. And so x dot would be the derivative of this function. Or x dot, because we have to show that a particular solution of the homogeneous system is given by this. So we have to show that that is the case. And so that can be seen as a derivative of this function. If you differentiate these, the integral goes away. And this is true since phi itself is a fundamental matrix. Okay, first we say since phi, this is how the proof goes, is a fundamental matrix. Is a fundamental matrix of X dot which equals AX. Okay, we have from a theorem, okay, the theorem 4.5. We have from theorem 4.5 that doesn't matter, but this as follows from the theorem, that actually we can find the derivative of phi. We can find the derivative of phi. Okay, good. Just 1 minute. Right. From the theorem 4.5 that phi dot. I need to get my pen back. Right, that phi dot, for example, of t is actually the same as a times phi of t. We therefore have we therefore have x dot p which is p0t phi inverse of s f of s ds plus phi of t. Okay, this is the proof. It comes in normally in the exam, so let's just discuss it. Right, times phi of t. Right, d dt p0 t inverse of s phi of s ds. So you have a phi of t p0t phi inverse f of s ds. So times phi inverse of t. Okay, so we have to show that x dot is this. That is how we prove this result. So x dot being that it would actually emanate from the fact that x dot can be written therefore as a linear combination of this, according to that assertion. So we have to show the derivative of the particular solution is this. Since phi is a fundamental matrix of the original differential equation x dot equals ax, we have from theorem 5 that for a fundamental matrix phi, it is true that the derivative, it is true that phi dot, it is true that phi dot is this. We therefore have um, that x dot can be written in this particular manner. Right, we therefore have that x dot can be written in this particular manner. Okay, we'll discuss this representation. Right, we'll discuss this representation. But most importantly, this simplification or this next step therefore becomes equivalent to that. That this integral here can be written in this form. I'll elaborate on this representation. But now in the end, we have that the derivative of the particular solution as a function of t can be written as this sum. Okay. Moreover, if this is the case, okay, we need to write more. Next step. Right, it means therefore x dot. So right, so it now you have this one is from t0 to t. Inverse of s ds. So this is, okay, so in other words, we agree that this inverse, this times the inverse function becomes the identity function. Because this phi is it's a fundamental matrix. A fundamental matrix is an inverse. So a matrix times its inverse is the identity times the function f of t, then it becomes f of t. And this is actually the representation we have. Plus f of t. By making use of the differentiation formula. Okay, it's something we call now by making use of the differentiation formula. What is the differentiation formula? All right, the differentiation formula is the partial derivative with respect to t So ds f of t primed of t. Okay, this is just a formula I'm writing here. Minus g, where g is a multivariable function of t. And once again, this is just a formula. It doesn't mean that it is the general sort of formula. Then you have, okay, can I just write this better? Can I write this better? Right, can I write this much better? So you have h of t plus h of t to f of t, which is g of this of t of s, t and s, and then you close like this, ds. Where where fg and h satisfy suitable conditions. Okay, I mean, you can just, this differentiation formula is optional. It's not, it's just an part of the explanation. Suitable. Okay, this is the proof. Obviously, you need to try and understand it as it is. You can, suitable conditions. You can like extend it so that it is um okay. We have shown. Okay, this one must be x dot. Okay, this proof is quite abstract a little bit. So okay, I need the green color. Right. So you need to just try and make sense of the proof. Right, but this is the proof, and normally it is what the in the exam must be proven. Right. So if f is continuous, why must it be continuous? Why must f be continuous? Okay, f must be continuous because um it must be integrated, and therefore, if it must be integrated, then integration of continuous function is what we study according to Riemann integration. Because a function that is not continuous often becomes not differentiable in some parts of its domain. Can give an example of a function that is not integrable. A function whose integral, well, is not Riemann integrable. Yeah, I need to state that because if you look at the function that is 1, 0, either 1 or 0, and then here, okay, and then here you take the complement. Okay, right. There is this function that is called the Dirichlet function. This one here that is either 1 or 0. It's a function that goes up and down. At a rational number, it is 1. If y is 1 at the rational number, it is 1. At the irrational number, it is 0. Then it is 1 again. It is 0. Then it is 1 again. Okay, this function is called the Dirichlet function. It is not continuous, as you can see. Well, continuity in the sense of you can use the calculus interpretation of continuity in terms of the limit, but it's not continuous because you can see it is a discrete function, sort of. But we require, therefore, that if f is continuous and this is a fundamental matrix whose inverse, because it's fundamental, the inverse exists of the equation this, then show that a particular solution of non-homogeneous system is given by this. Right. So in the end, if you look at the proof, obviously we have to show that the derivative of the particular solution is actually given by this. And if you check very carefully, x dot equals axp plus f of t, that's what we've shown. Right, the abstract nature of the proof, it's a very interesting one. So if phi is a fundamental matrix of this, x dot equals ax, we have from theorem 4.5 that theorem 4.5 says that if phi is a fundamental matrix, then wherever there is x, you can replace the x by the fundamental matrix. It's a theorem 4.5. And we therefore have that. We can therefore be able to write this expression that x dot can be written in that form. What format is this? Right, so it can be written as a summation of this. Right, so x dot therefore can be written as a summation of this because x dot is actually that. And which means that if x dot is actually this and it can be written in this form from theorem 4.5, then this summation is itself a possible summation, because in the end, what you're then getting is that x dot is this, and if x dot is this and phi dot is that, this becomes phi and this becomes like a matrix, and this itself has a vector representation equivalent to a matrix representation, and therefore it actually, this representation becomes equivalent to this. This here, the question is, where does it actually come from? We said on the next page, it comes from the formula. By making use of the differentiation formula, this differentiation formula, that if you have a multivariable function, it expands to this. That is the general formula where the f, g, and h satisfy suitable conditions. So it is actually what has been used in this case to achieve this, the differentiation formula. We can only spend some time to verify and show how obviously that has been used, that formula. But in the end, what we're then getting is that we have this. And this expression is therefore equal to phi inverse of t times f. And also this here has just been carried forward. Right, so if that has been carried forward, because this phi inverse of S becomes phi inverse of T times F of T. Why is this? This can be seen even from the differentiation formula. Many ways to look at it. Because if you differentiate the integral, it spreads to this. If you differentiate the integral, it spreads to this. But obviously, G is a multi-variable function here. So if you look very carefully at, well, the function we're dealing with here under the integral sign is a function of S, which is a simpler case. Which is a much simpler case. Next. So I would say that obviously the theorem has been proven. You can always try to make sense of it using the formula at the back. Next point. Right, next point is this one. So let's get the proof of this one. This solves this one. Okay, this is a bit easier because in application of the theorem. By and large, even application of the former result, we've just proven. Okay, right. How do we prove this? We prove it. Oh, how do we solve this? How do we find a general solution? We find it as follows. We find first the eigenvalues. So the characteristic function. All right, the characteristic function of the matrix is so okay. This is the matrix A we're dealing with. We've already seen this is like X, exactly what we have seen. All right, is exactly X as a function of T, which is AX plus F of T. So like X dot is actually this. So the characteristic, so this is like the matrix A, and then we are subtracting the identity lambda times identity. But yeah, this is not, it's obvious. It's always like this. So it's always going to be the main diagonal entries minus lambda, like we saw in linear algebra, and then 1, 1. Okay, we take the determinant of that, and this becomes sort of the characteristic function of the matrix. 1 minus lambda squared, and then plus 1. So, okay, we expand this. If you expand this, what you get, you can, it's obvious, you can write it as minus 2 lambda plus 1, or the other way around, because the lambda is after the 1, and then you add 1. Plus 2 equals 0. So that the eigenvalues, yeah, okay, right. Right, so that the eigenvalues are given by, okay, what are they? Okay, you can use the quadratic formula to solve this one. So it's going to be minus b plus or minus the square root of b squared 4ac over this. So we continue. We continue. We continue. Right. Okay, yeah. Yeah, I'm in class. Can I give you a call when I'm done with my teaching? All right, that's fine. That's fine. Okay, thanks. Right. So what do we get here? This is 4 minus, it's 4 minus 8, which is like minus 4. Can just write that step over 2. Okay. Just write some trivial step. The square root of that is 4i over 2, 1 plus or minus I. These are the eigenvalues of the matrix. Then we just need to get the eigenvectors of the matrix. Right. Okay, this came in the exam, question 3, part B. So this way the eigenvalues, and then we just need to get the eigenvectors. Let's just practice with this one. So for lambda equals 1, normally these become complex conjugates. For lambda equals 1 plus I, the associated eigenvalue is given by, is given by, okay, so you have this one, 1 minus lambda minus 1. Yeah. Okay, let's just write this step. 1 minus lambda minus 1, and then 1 and the 1 minus lambda, you can write like this. And this one is multiplied by some vector, because we want to get the eigenvector. And this is always equal to the 0 vector. Okay. So you have this. So you have 1 minus 1, which is 0, and then is minus I. Okay. You always write this. Right. So now we write the augmented matrix of this associated system. Right, so now we have this. So let's add this. So this is going to be row 2 plus I row 1. We multiply this and you add. You multiply this by I. Right, you multiply this by I. What you get? We get a 1 and then becomes 0. Like so. And then what does this give us? V1 is going to be I V2. V2 equals V2. So now it's, you have this. I1. Like so. Right. Okay. The practice is I'm going to write that. We say we take different from yesterday's real case, real solution case, where we had real eigenvalues. But here we have the complex ones. But obviously we're doing the eigenvalue eigenvector method. But now here we're using we are solving a different initial value problem using a different method of fundamental matrices. So now in the case of the fundamental matrices, you can see that we take V equals this V2 to be 1. We made it a constant yesterday, but yeah, okay. And so that um, what is this? Okay, it means therefore, so you have that if this is 1, then you have I1. So um, then you have I is an eigenvector. Okay. Okay, this vector can be written like that because you separate the real part, which is 1 and 0, and then the I part is separate. And we factor out I from inside the vector, and we get that. So we always do write the complex vectors like that. Um, okay, I want to write properly. So now this vector is I1 equals this. Right, vector equals I1. Which is 0, 1. Um, you have this. All right. Okay, you have this. Okay, um, B is that. There's a theorem called theorem using theorem 3.19. It is on page 32 of the study guide. Hey, what does the theorem say? It says therefore, okay, we dealt with only one eigenvalue, and then we also found the associated eigenvector. We did not go to the other one. So yeah, because they're just conjugates of each other. So we just look at one complex case, and the other one is automatically covered. In which case, according to that theorem, then we shall have two solutions. You shall understand this is not okay. Maybe let me write that theorem down. Just 1 second. I'm just going to write it on the screen, page 32 of the study guide. I'm just going to write it down so that you can just see. You can just see the theorem because we're going to use it. Is very, very important here. Right, where is the thing now? Okay, I'm just going to write it now. I'm just going to write it now. Um, so, okay, the theorem says lambda is A plus IB. The eigenvector, so this is the eigenvalue. The eigenvector, it is V plus I. So then it's x1 of t. Okay, so the solutions are two of them. So this is e to the at. I'm just writing down the theorem 3.19, right? So it puts the vector v here, cosine bt, sine bt, x2, e to the at, v, sine bt plus w, cosine bt. All right. Okay, the theorem says if the eigenvalue is this, then the eigenvector is this, which is what we saw. Then we can write the solutions in that manner. So in this case, you remember that we chose this eigenvalue, and this is the eigenvector. So how will the solution be in view of the theorem? So we'll just follow this theorem and just plug in the the things. Okay, but also here it would mean a couple of things, but it would mean this vector is having a v here and a w here and an I. So um okay. Okay, right. So we are right back. Just 1 second. Okay, all right. What is x1? X1 of t. We just use the theorem 2.19 to write the answer. And we actually pretty much be done. So what is this? This says e to the at, e to the t. Okay, you can write round parentheses or square parentheses. So this is 0, 1. So you have cosine t, 1, 0. Okay, you put a minus there, then it becomes sine t. Why like this? Why is it like this? Because um, the a is 1 from the 1 plus I, and then the b is also 1, coefficient of the marginal part. Okay, these can be written together. We can multiply out everything, and this can be written as e to the t into, so this is minus sine t, and then this is cosine t. So um, the second one is going to just be having the sign first and then a plus. So the v is going to be exactly, we start obviously, we write the v first, okay? They both have v first. V is 0, 1, and then you have the sign of the bt. B is the coefficient of the I, which is 1 in the eigenvalue, giving us a t plus. Okay, the w is this associated with I, which is 1, 0. Cosine t. So um right, so you have this. Okay, from this we say two real solutions. Two real solutions are as follows. Okay, just here. Two real solutions are, what are they? You can write them like this. And find t while a fundamental matrix, right, while a fundamental matrix is okay. What is the fundamental matrix? Okay, look at how we construct the fundamental matrix like we saw in the proof of the previous theorem. It is minus sine t cosine t cosine t sine t. E to the t. Okay, this is the fundamental matrix. We just made these columns, the solutions, made them columns. Okay. And the fundamental matrix is called phi of t because the components are functions of t. The components are functions of t. With phi of 0. Okay, if now we have the initial conditions. What are the initial conditions? Then in initial conditions x0. Yes. So the t0 is 0. So if the t0 is 0, then you put 0. Okay, this becomes 0. 0. Okay, now we have then the inverse of this matrix. What is the inverse of this matrix? Okay, the inverse of this matrix is it's 1 over the determinant of the matrix, 1 over the determinant of the I0 matrix. Then what we do here, you switch these two. Okay, and then you find this is a -1. Okay, so multiply out. Okay, so yeah, the inverse is, okay, I meant the inverse here. So this matrix is this, and the inverse is that one. Okay, we need to find the inverse because we need to find a normalized fundamental matrix, because this one is a fundamental matrix, but it's not normalized. We need to normalize it. So to normalize it, we find the inverse like this. Now we need to normalize this matrix. Okay, so the normalized fundamental matrix becomes what we write next. Normalized. Fundamental. Matrix is. So this is how we normalize it. How to normalize the matrix? We multiply like so. Right, so to normalize it, we take 5 minus t, we multiply by the inverse both sides. And this right, the inverse we already know, phi inverse of 0, 0, 1, 1, 0. Okay, and then this one in the middle is going to be, we remember that phi of t is the same as what? Just going to write it down. We made those eigenvectors, we made them columns of this matrix, and such a matrix is called the fundamental matrix, where the eigenvectors themselves became what? Became columns. So, okay. Now this is the inverse. And therefore, this one, 5 minus t, what does it mean? Okay, it means that wherever there is t, we make it minus. So let's just write a little bit of just some steps trivial, like minus t. Now I can write quickly. And then we have minus t. So we have cosine of minus t. And then you close 0, 1, 1, 0. Okay, let's just multiply these matrices out. Okay, if you, the negative diffuses goes through a sign, sign is odd, so that this is sine t. Cosine is an even function, so cosine of minus t is just cosine of t. The sine is an odd function, so this becomes minus. Okay, so multiply these. Just first multiply the first two. This by that, is actually cosine t. This by that is minus sine t. This by that is sine t. This by that is cosine t. So you have this and that is minus sine t. And this and that is cosine t. This row and this column is cosine t. This row and this column is sine t. Okay. What is all this here? We check this is exactly this matrix. So in this case, this is actually phi of t. Hence, um, hence the phi inverse is e to the minus t minus sine t cosine t cosine t sine t. All right, next. Now we need to, okay, this is a bit lengthy, yeah, but now we need to write the particular solution. Let's just continue to on the next page, perhaps. Yeah, next page. Then the particular solution. Particular solution is therefore xp, which is phi of t, which is this phi inverse. Okay. This is the formula for the particular solution that we use. F inverse ds. Okay. We recall that phi inverse of t is e to the minus t minus sine t cos t cosine t sine t. xpt phi of t Okay, now this phi inverse now of S, this is of T, but now in the formula we have the symbol S for the particular solution. So it means that we're gonna replace every T by S. Okay, let me not congest things a lot. Let me just remove these parentheses here and write e to the minus S here, minus the sine of S, cosine S, cosine S, the sine of S. What is Fs? Um, okay, what is Fs? Right. You'd remember um, the representation we got. Right, the representation that we got. Because Fs becomes what we achieve from the equations themselves. Um, Here is f of t. F of t is 2 cosine t sine t e to the 2t. So we're gonna just plug it in there. Okay. So what is it? It is 2 into cosine s sine s. E to the 2s ds. Okay, so you have that. Okay, let me remove this one. Okay, and then you put 2 here. Okay, the 2, 5t, the integral from 0 to t. Mhm. Okay, e to the minus 2s and, oh, e to the 2s and e to the minus becomes just e to the power s. So this and that. Cosine s sine s plus sine s cosine x s sine squared s plus cosine squared. Okay, if you multiply all these matrices, this is what we get. Okay, it's easy to multiply this. You have this times this, which is minus sine cosine, cosine sine. Then you multiply this with this, which is cosine squared, sine squared. Okay. Now, what is all this? Okay, 2 into 5t. So this becomes 0. Yes. Okay. Right, what is this? Mhm. So it's 2 5t. And then we have big bracket. Right, the integral of this one. Okay, first the integral of e to the s becomes just e to the s times 0 becomes 0, and then 0 to t. The integral of e to the s is e to the s times 1, 0 to t. Two phi of t. So which means e to the t minus 1, like so. Almost done. Um, and this means the particular solution of t is 2 phi of t into 0 e to the t minus 1. That is the particular solution of the problem. And then we continue, but it's not, it's written in terms of the fundamental matrix phi of t. So we must substitute the particular solution as a function of t, phi of t, which is 0 e to the t. So phi of t, what is the fundamental matrix? Okay, we remember the fundamental matrix, we got it before. Okay, I'm just going to write it down. Is sine t. We got those eigenvectors, and then we just made the columns of the matrix, and this matrix became what we call the fundamental matrix phi of t, cosine t sine t. Okay, this is the matrix, but it has e to the minus t from the other page. Okay, so minus 1. E to the minus t. So we multiply this and that. So this times that is 0, and then we just have um, okay, let me see. Excuse me. This one is a plus t, please, from the fundamental matrix. It's plus, so I can remove this. So with this and this. This times that is 0, and then this times that. Okay. Um, yeah. 0 and then this, which is cosine t to the 2t minus e to the t. Yes, Bupilo. I'm still in class. As soon as I'm done, I'm gonna get back to you in the yeah. Soonest time. Soonest time. As soon as I'm done. Okay. E to the t, and you close. Okay, I'm gonna get back to you as soon as I'm done. So you multiply this here. Right. So multiply these with that, and multiply these with that. Right. This is going to become 0 sine t. Um, um, so you have this. Okay, sorry. Just writing that this properly. Multiply the first one, so it became cosine t. Bottom row became sine t there, like this. Okay. All right, you continue, please. We are finishing. Sorry that this problem is dragging a little bit. It is sine t there, sine t. Okay, this is what? The particular solution. Okay, in the previous slide, we stated it as as a what? As in terms of the fundamental matrix 5T, which is formed by the columns of the eigenvectors. But now we have the particular solution obtained using the formula we have. What is the formula? It is exactly the formula for the particular solution, this here. Use it and integrate it, and we got the result. Okay, this particular solution is not the only solution, and hence now we have a general solution. Hence the general. Solution is given by um right at the bottom here is given by just x of t equals c1 x1 of t plus c2 x2 of t plus c1 cosine t plus c2 cosine t sine t. So ah okay, can I just write at the bottom here? Sorry. So that we have c1 minus sine t and cosine t. and then e to the t. I'm just writing exactly this here. Again, C2 cosine t sin t. E to the t plus 2, and then now it is e to the 2t cosine t minus e to the t cosine t e to the 2t sin t e to the t sin t, where Q1, Q2 are arbitrary. Arbitrary constants. Okay, this is the solution. So the solution becomes the first one, we got x1 of t, and then we got x2 of t from the complex eigenvalues into the eigenvector that we got. And then we got x1, x2, and we put them there. So I need to remove this because I wanted to write it here, but I realized that it would just go to the margin too much. Right, so I decided to write it underneath. But yeah, this is the solution to the problem. This is a general solution. It combines a particular solution that we obtained with the integration and the fundamental matrices. But these uh, x1 and x2 came from what? They came from the original um, system, x1, x2. Now we've just put c1, c2 there. But those ones came from the these ones. They came from the eigenvector that we got because the complex vector and the complex eigenvalue produced x1 and x2. And then now they actually therefore form part of the what we call the complementary function, because every general solution is formed by two types of solution, the particular solution and the complementary function. This becomes the complementary function, the particular solution. So we have that. So this is the answer to the problem. Right, quickly getting to the problem. The problem is use the result of 3a to find the general solution to this. 12 marks. Okay, it's a bit more excessive, I think, for the marks, and time becomes a factor. Now we continue to solve more problems. Right, now here is another type of problem that we actually need to solve. And this kind of a problem that need to solve is write the equation below as a system of two first order differential equations and then find the series solution using the power series method. Okay, now let's look at these carefully and see how we can be able to solve this particular problem here and what we can be able to make as the answer to this. Okay, the power and find the power series method. Okay, this is also a bit lengthy, 40 marks. So yeah, it's a marathon, and we are equal to the task at hand. This is what we do to solve this particular type of problems. We let x dot be equal to y, full stop. Then we have y dot, which equals, okay, y dots now will become x double dot. And what is x double dot according to this? X double dot according to this is minus 2x dot. X double dot you transpose. Okay, we are starting the solution in order. And what is x dot? X dot is y. So yeah, like this. So the second order, right, because write the equation below is two-phase order and then write a series. Okay, so the second order initial value problem becomes a system of two first order and first order equations. And that would mean what is x dot? X dot is y according to this. In other words, the derivative, this is how we write the derivative in this section. The derivative of the x is y. But we also have y dot, which is minus 2y, with x0, 1. And then what is x dot? X dot is y. So this can also be written as y at 0 is minus 2. By putting x by putting the vector x like that, the problem can be rewritten. You can write it in vector form. The problem can be rewritten. Can be rewritten as right. Rewritten. Okay, we have just need to be faster. Right, need to be can be rewritten as right. What is the problem now? Okay, because we're from a different page, I'm gonna do it step by step to make sure that we get the problem right, that we write the correct thing. So this is first x dot equals y. Y dot equals minus 2y. X dot equals y and y dot equals minus 2y. Okay. Mm, we have already said. Okay, yeah. I'm trying to write this as a matrix thing. Okay. Um, what did you say? We said x dot, okay, okay, the initial values. So x0 is 1 and y0 is minus 2. So x of 0 is 1. Y of 0 is minus 2. Mhm. Hence, okay. Now let's write this. Okay, remember that the vector is this, is that. So x dot, okay, let me move this bracket closer. This can be a little bit interesting to play with in terms of the notations because, okay, if x is this, then x dot is what? X dot is, you differentiate this vector, is the same as differentiating the individual components, like so. So, so what is x dot? It's y. Y dot is minus 2y. Okay, like so. Okay, this power series normally has a bit more work, so yeah, we'll try to be faster. Okay. Now we need to write it in the matrix notation. We need to factorize it and put x, y here. So what must this matrix be? Okay, let's think. So x dot must only be y. So what do you do to get only y here? So you must put 0, 1. You can see when you multiply this with that, it's going to just become y. And then the second one must become minus 2y. So which means you will have 0 minus 2. So that when you multiply this with that, it becomes minus 2y. This is the matrix 0, 1, 0, minus 2, x. So, okay, need to remember this. Um, so what is x0 now? X0 would be, let me write it step by step. Right, so x0 would be this one. would be x0, y0. Right, so x0 is 1 minus 2. Okay, so x0 is this vector. Next. Right, here comes the, okay, and we can write and say since all entries are constants. Okay. The matrix itself is analytic. Since all entries are constants, I'm writing twice. Right, since all entries, right, are constants. All right. The matrix A is analytic. At t equals 0. Okay. Yeah, because it is at 0 here. That's why t equals 0. According to the problem, and thus the sum. Okay, we're able to find the summation. This one, k equals 0. A sub k, t minus t0, k, can yield the constant matrix can yield the constant matrix like so. Since all entries are constants, the matrix A is analytic at t equals 0. Thus, the sum can yield the constant matrix that. If and only if. A1, A2, A3 are all zero. Okay. Are all zero. Okay. Not writing clearly, but yeah. Okay. Are all zero. If and only if A0, okay, A1, okay, A1, then A2, comma, A3 are all the zero matrix. Are all the zero matrix. are all the zero matrix. Hence, hey, okay, this is how we start. We start with the matrix A0 and call it A. This is the power series method. So that this is 0, 1, 0, minus 2. And then we write um, okay, this one we write like this. And then the understanding therefore is that if you continue with this pattern here, just write closer. I wasn't going out of space here. Okay, if you continue with this pattern, okay, this is the last question, please. It's going to be 1 over this n is going to be n factorial. And this is going to remain this matrix 0, minus 2. This one is going to be nx0. So this one is the matrix A we got with the power n x0. Okay, so this can be further written like this. So this one is a recursive formula. It's a recurrence relation. The recurrence relation, and it can be written like this through, it has this representation. It has this representation, always this representation. The n becomes n factorial power n, and the x minus 1 becomes x naught. Now, from, okay, now we need to make the step here. Okay, need to here at this point, when it comes to the power series method, you need to be very, very observant. Like, you need to be observant in the following manner. What is the matrix A? Is this one. It's 0, 1, 0, minus 2. And then, okay. Okay, now, this matrix x0 is 1 minus 2. Okay, 1 minus 2. Now, multiply A with the x0. What is the answer? Okay, this row by this column is going to produce minus 2. This row by this column is going to produce a positive 4. Okay, normally we need to do a little bit more to see the pattern here. Let's do up to like 4 of these. Now let's do a squared. A squared x0. Yeah. What is a squared of this? Well, it's just the square of the matrix A. So if you square the matrix A, okay, yeah, we just have no choice but to write the matrix A twice for a start. And then there will be, okay, this is the matrix A, this one, but we're going to square it. Okay. Mhm. A squared x naught. Multiply this by that. Okay. We're squaring the matrix A. So this by that is 0. This by that is minus 2. Okay. And this one is 0. And this is 4. We multiply this by that. So this is 0 and then 4. This by that is minus 8. Like so. Let's do the cube. So we're going to do a cubed x naught. What is x cubed? A cubed, excuse. So a cubed can be seen as, all right. There are many ways to think of that. Can be seen as a into a squared x naught, which is now this one is we already know, but the matrix A is this one. Many ways to quickly do this one. All right, that is the matrix A, 0, 1, 0, minus 2. But the a squared x naught is 4 minus 8. And what is the result? Okay, if you multiply this with that, is minus 8. This with that is 16. Okay. So let's do one more. A4, a to the fourth power, x naught. Okay, we are finishing, please. This one is going to be a into a cubed. Okay, this is called the power series method. And then now the a is this one, 0, 1, 0 minus 2. What is the a cubed? 16. So 0 in that, 0 in that. We have this. Any general pattern? Let's check. Ax0 is minus 2, 4. The square, it becomes 4 minus 8. Okay. Right, this normally obviously becomes an interesting, so it becomes a number patterns problem from school because the minus 2 becomes 4. So it's like it has been squared or something. And then here is cubed. So this is like 2 to the power 1 and then here, and then it's cubed, and then to the fourth power. Okay, it's the pattern. There's something obvious you can see. So yeah. And then now let's look at the at the at the at the bottom ones. At the second entries, the for ax0 is 4, the square part is minus 8. Okay, so 4 becomes minus 8, and then it becomes 16, and then it becomes minus 32. So what kind of a formula is this? Is it geometric? Is it a cubic thing? And now we're going to say this means, okay, we're writing here. And then, okay, this is just, okay, so what is a to the power k? A to the power k of x naught. What is it? Want to write it down? Okay, at 1, it becomes -2. So yeah, the first one is pretty obvious because it appears that it's -2 to the power k. So that when it's a to the power 1, then it's to the power 1, which is -2. When it's a squared, then you square -2, you get a 4. When it's cubed, you cube -2. -2 cubed is -8. -2 to the fourth power is 16. Okay, let's deal with the second one. 4 becomes -8. First term is this in terms of sequences, then you have -8, then 16, then 32. Okay, the signs sort of alternate. So, which means that at 2 it's minus now. At cubed is plus. At 4 is minus. So it appears that in 4 and then it's doubled, and then further doubled, and then further doubled. So that the cube is not even multiplied by 3. Okay, let me just work it out here. Did not do this during my time. Right, so you have 4 minus 8, and then 16 is a sequence, and then minus 32. What kind of a pattern is this? Right, so you can even remove the signs for a start and look at these to simplify issues, and then we'll take care of the signs. If you divide this by that, it's 2. This by that, it's 2. This by that, it's 2. Wow. So it's geometric. From high school, the geometric nth term is this one. Okay. The first term is 4. The common ratio, if you divide the second by the first, becomes 2 to the power n minus 1. This becomes sort of the pattern, you see. Okay. And this thing here can also be written as the 4 can be written as 2 to the power 2. 2 to the power n minus 1. So this can be written as 2 to the power n. You add the powers, it becomes plus 1. So that when n is 1 at the beginning, it becomes 2 to the 2, which is 4. When n is 2, it becomes 2 cubed, which is 8. 3, 3 plus 1, which is 4. 2 to the power 4 is 16. Okay, 2 to the power 5 is 32. But now we work out the signs. What are the signs? Right. So, which means that doesn't matter. We can put minus. Right. So it's gonna be 2 to the power n plus 1. So is n plus 1 here. But what power can we put on this? Because to take care of the alternation part, but at 1, you can put, let's put k plus 1 and see what happens. Okay, because if you put 1, then it's going to become plus. At 2, it's going to become 3 here, which is minus. At 3, it's going to become 4, which is plus. The power of the minus 1. At 4, it's going to become 5. We're good. So this is it. This is the general formula that we want. Right, after we got this general formula, we move to the next page. A to the power, okay. A to the power k x0. Okay, minus 2 to the power k. Minus 1 to the power k plus 1, 2 to the power. What did I write here? Okay, I wrote an n plus 1 here, but it must be because we're dealing with the case. So it must just be a k here. Okay. Right, we're finishing, please. Sorry that we've taken so much time on this problem. Power series method to the power k, like this. Okay. So the power k plus 1. Okay. Yeah. So you have this. Hence we have so k0. Okay, I need to change. Let me write another step. We need to use these here. Okay, but first, even this, let me remove. Okay, so I want to write that these together with this is step we wrote where we said xn is equal to 1 over n. Is it 0, 1, 0 minus 2? So you have this 1 over n factorial. Right. Yeah, so it's 0, 1, 0 minus 2. Don't need to write the wrong thing. Yeah, 0, 1, 0 minus 2. I'm writing this step, so it is this and it is that. So that's what I'm writing. So it is 1 over n factorial, then it is 0, 1, 0 minus 2. Then it is raised to the power n, then x sub 0. And then it is 1 over n factorial, which is a to the n x0. So that x of t mhm, that's not what I want to write. Okay, I want to write the fact that we have these, but now this one we can replace by this. So thus, okay, it means therefore that xn can be written like this. So it's 1 over n factorial. And write like that, it's okay. And then here we can change the things. Ordinarily, okay, I'm finishing, doesn't matter. These are dummy symbols, but I wanted to maintain the culture of writing in this course. And the culture of writing is to make these ones k. Okay, so we'd have k then k. Okay, so yeah, if xk here is going to be that one. So we have this. So is one of the that. Okay, and then yeah, this what is we put this matrix. We put minus 2 to the power k. Okay, even these, because now if you look at the powers like this, with the powers like this, they have the same power. So you can write it as minus 2 to the power k plus 1. Yeah, and it means, just make a note here, that this one to the power k minus 2 to the power k plus 1, like so. Okay, so yeah, it can be written like this or can write like this. You can put the minus 1 inside there, making it more compact. And we can therefore have this. Right. Okay. Um, right. So we continue. Okay, we're finishing, please. We are finishing. This is the power series method. Normally we need to, yeah, it's just the last couple of steps that we need to deal with. Okay, if we have these, what do we do? Okay, so we have that. Okay, hence All right. What do we have? Hence we have x that, which is the infinite series, the summation k equals 0. Xk e to the k. So you have k equals 0. Okay. So yeah. So what is xk, x sub k, t to the k? So x sub k is this. Then just multiply by t to the k. So it's going to be 1 over k factorial from this, the vector minus 2 to the k, and then minus 2 to the k plus 1, then t to the k, like this. You just put it to the k in front, like so. Okay, this is pretty much towards the end of this. Can we do some factorizations here? Yeah, we can. What can we factor out of this? Common factor from the matrix, there is minus 2 to the power k. So minus 2 to the power k. And now you have 1 here minus 2. Then you have t here to the k. So we have this. Now, what is all this here? X of t. We are finishing. This is pretty much the last step. 1 minus 2 is the common vector. It has nothing to do with k, so it's a constant. It is vector, so it can be pulled out. And we have the infinite series, k equals 0. We have minus 2 to the power k. It is divided by k factorial. And then there is t to the power k, like so. And this is the final answer. How do you know that this final answer is correct? How do you know that is correct? Okay, what is the zero vector? Zero vector, x. So let's do a check. I'm going to check in red. We can do a check. Okay, it's just the last step. Okay, if you look at x0 like this, x0 is going to be, according to this, 1 minus 2. Okay, t is 0, so it's going to be 0 to the power k. And this is going to be 0. And then you are adding zeros. Mhm. All right. No, yeah, but not everything is going to be 0. Okay. So there's a small little trick in the sum. Um, First, I'm going to leave it as k. And then the first term is going to be 1, which is the one we want, because you have t to the little k. And then this one is going to be 1 minus that, 0. Okay. Um, okay, if you put 0 is 1, and then, okay, okay, this is still t here. Okay, we're done, but yeah, it's going to work. I'm just having the check, but yeah, it's the correct thing that we got. Right, so this one is x of t. It's exactly this, but now we are just expanding to check. So if you have this summation, it's going to be 1 plus the summation, plus the summation. Now the summation is going to be from 1 to infinity, minus 2 to the k, t to the k factorial. So yeah, just a little thing here. Then we have x0 is equal to, okay, if t is 0 now, this term is going to be zeros everywhere because it's going to be a function of t this, but this one is going to be a constant. So it's just going to become 1 minus 2 into 1. So you have x of 0, which is 1 minus 2. Okay, so x of 0 is 1 minus 2, but yeah, in the problem, we were able to convert the problem to that. Was 1 minus 2. So we found the x0 vector. So the x0 vector was 1 minus 2. So it's 1 minus 2. So we've checked that the actual solution itself is satisfies the initial value of the, or is consistent with the initial value of the problem. And therefore, this is the solution that we got by using the power series method. And the question was, we're just concluding, please. The question was, write the equation below as a system of two first order differential equations. We wrote them first order. Then find the series solution by using the power series method. Write your final answer in terms of an appropriate exponential function. Okay. In terms of an appropriate exponential function. Right, so that is what we have. Okay, I want us to write the final answer as an appropriate exponential function. What would the appropriate exponential function? Let's check. Right, so we get this answer. Let me write this on the next page. X of t. Okay, is equal to 1 minus 2. Then you have the summation. So it's minus 2 to the k and then t to the k. Okay. What is the appropriate exponential function? Obvious. Right, it's 1 minus 2, the infinite series. So you can write this like so. So you recall that in calculus, recall that, for example, hello, hello, my dear. All right, my dear. Recall that. Okay, we are finishing in the next 1 minute, please. 1 minute. Hello, my dear. Okay. Okay. Yes. Yeah, yes, yeah, go, yeah. That's fine. That's fine. Um, okay, 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 okay. We're done. We recall that in mathematics, e to the power t is 1 plus t plus t squared over 2 factorial plus t cubed over 3 factorial and so on. Okay, so this is the summation. So you can write this k equals 0, and then write here t to the k factorial. Okay, so if this is the exponential function, so now this here can be written as follows. So is 1 minus 2. Okay, so it's e to the t. So which means that it's just going to be e to the, because if this is t, then it becomes the power. So here, what did I write here? Wrote a k. It must be t here. It must be t. So that what we have is that it becomes e to the minus 2t like this. So this has been written in terms of the appropriate exponential function. Hence, x of t is actually the same as 1 minus 2 e to the minus 2t. All right, so this is the answer to the question written in terms of the appropriate exponential function. Okay, I'm concluding, please. We're just done, please. Let me see. So write your answer. Yeah, so you have this. Write the equation below is a system of two first order differential equations, and then find the series solution by using the power series method. Write your final answer in terms of the appropriate exponential functions. And we have done that. And for 14 marks, we are done. Okay, so this is going to be the last question for today. And I must plan to see you tomorrow. I must plan to see you tomorrow when
Yeah, hello.
yes, please. Any question? Right. I'm gonna see you tomorrow. At what time? Let me see when the exam is gonna be. I think the best time is just 6:30. Um, I know that maybe you don't like late hours, but can I request that we do 6:30? Um, Tomorrow to do more things. There's still autonomous systems. You need to discuss those autonomous systems. So can I request that we meet at 6:30 tomorrow? In the early evening, and we try and see. We are finishing already. We're becoming familiar with this, but we have to look at autonomous systems and also we have not looked at repeated routes as well. Those kinds of things. So all right, yeah, please. I will see you tomorrow at half 6. Okay. Thanks a lot. See you tomorrow. More autonomous systems and other things. Thank you.